Today we start working or looking at the integral as net change, and one of the big things we're going to be working on through this idea is the idea of relating velocity to the integral. Okay? And that's going to be a very important topic as we continue to prepare ourselves for the exam in the spring. And if you remember how we started our whole discussion of the integral, remember when we talked about a train going at a constant speed of 75 miles per hour, and if I wanted to know how far it traveled in 3 hours, then we would look, if this is a constant speed of 75, and let's say the train left at 1 p.m. and then we looked at where it was at 4 p.m., we could consider this an area. And so what we found out was that if we integrated a velocity, now this is just in general, if I integrated a velocity, I could get a distance. All right? And so we're going to expand that idea today. But before we do that, I want to come back to our particle. Let's consider a particle, all right, moving on a horizontal plane. Remember, we did a lot of those problems in the fall, working with velocity. And we're just going to draw a simple graph here. And let's say that the particle starts at 3. Okay, we're not worried about y values here, because we're just talking about horizontal values. Let's say it starts at 3 and moves to the left 2 units. Okay? Of course, we would think of that as a -2. Move to the left 2 units. And then from that point, let's say the particle is now here. Now the particle moves to the right 7 units. Okay, so now it moves to the right 7 units. Now, it doesn't take a rocket scientist to figure out where we're at now. We moved to the left 2 units and we wound up at 1. If I move to the right 7 units, I'm at 8. This 8 is the position of the particle, all right? But what if we wanted to talk about the displacement of the particle? And I know you've talked about this some in physics, those of you that are in physics. But if we talk about displacement, we're talking about what is its net change in position. Okay? What is its net change in position? All right. Well, if we talk about its net change in position, it started at 3 and wound up at 8. So I think we can see that the net change in position is 5. All right. Or we could think of that as it moved to the left 2, which is a -2. -2 plus the 7 it moved to the right gives me 5. But one other idea is total distance. The total distance it traveled, all right, is different than the displacement. In this case, it moved to the left 2 and then to the right 7. So in reality, we have to think of the absolute value of -2 plus the absolute value of 7 and see that it moved a total of 9 units. All right, so when we consider total distance, we're considering absolute value. Okay? And in the fall, we did some work with velocity functions. Let's just consider, the velocity function. And let's say that my velocity function, v of t, is t squared minus 8 over the quantity t plus 1 quantity squared. And let's say we're talking about the time interval from 0 to 5. Okay, so we're talking about between 0 and 5 seconds. All right, now I don't want to spend a bunch of time here because this is all review. But let's just kind of review a few things about this function. If I were to calculate v of 0, okay, if I were to do v of 0 on this problem, I would get negative 8. So that means at time 0, okay, the value of the velocity function is negative 8. What does that mean? Okay, remember what that means? That means at time 0, it's moving left 8, and let's say this is in centimeters, 8 centimeters per second, moving left. Remember, if we have negative function values, the particle is moving to the left. Well, let me just kind of sketch the rest of this graph. Okay, let's say that the graph, that's kind of what this graph does, and it does some other things over here. But it crosses the x-axis at 1.2545. Now let's remember what we've learned in the fall. Okay, here the velocity values are negative, which means it's moving left. When it changes sign from negative to positive, all right, at this point the particle has to be stopped. All right, and then from this point on, it's moving to the right. Okay, and so that's just a quick review of some of the things that we learned in the fall. You know, and I could come clear over to the end of my time interval, clear over to 5, and I could find v of 5, and I'm going to save you the time. That's 24.8. Well, what does that mean? This is positive, so it's moving right. Okay, 24.8 centimeters per second. Okay, and that's all review. Now, as we start to relate this to the integral, though, all right, I want you to keep in mind something that we talked about in the fall. We started with a position function, and we said if I do the derivative of position, I get velocity. And if I do the derivative of velocity, I get acceleration. Now that we know what an integral is, and we know it's the idea of an antiderivative, I think it makes sense that you can see if I, by the same token, if I integrate acceleration, we can start working back up this way. If I integrate acceleration, I'm going to get velocity. And if I integrate velocity, like I said, we're working back the other direction. If I integrate velocity, I'm going to get position. Okay? And so, you know, it's very important to keep that in mind, the relationship between going forward, taking derivatives, and going back this way, integrating. If I integrate acceleration, I get velocity. If I integrate velocity, I get position. Okay? So, let's come back to that function we worked with a second ago. The v of t equals t squared minus 8 over t plus 1 quantity squared. Okay? And let's also add this little tidbit that it is modeling horizontal movement. Okay, we're used to dealing with that. But I'm going to add a little piece of information here. Let's say the initial position, that's going to come up several times the next few weeks. If the initial position of the particle, all right, at time 0 is 9. Okay, or in other words, we could think, remember the position function we called s? We could think of it as s of 0 equals 9. This is a location. Okay, that's the location of the particle. So, what if we were asked, what is the particle's position at a time of 1 second and at a time of 5 seconds? Well, remember what we just learned. Okay? If I integrate velocity, I get position. So I think it makes sense that we're going to have to do an integral. All right? So if I want to find out the answer to this first question, well, I need to do the integral from 0 to 1 of t squared minus 8 over t plus 1 quantity squared dt. Now, I'm not going to spend a bunch of time on the integration of this. I will tell you that we would split it up into two different integrals. And on the second one, I would pull out an 8, and I would write this as the integral of t plus 1 to the negative 2. And we'd have to do a substitution to let u equal t plus 1, and so on. But on both of these, we're going from 0 to 1. Okay? And just for the sake of time, I'm going to move down to what the answer of this is. Okay? The answer is negative 11 thirds. Well, what does that answer mean? Okay? Well, if we go clear back to the start of what we said today, okay, it is displacement, all right? Because we did not do absolute value, we just integrated velocity, all right? And if I just integrate velocity, it's going to give me the displacement of the particle, all right? So where is it then at time 1? Well, where did it start? It started at 9, okay? So if I want to know where it's at now, I need to take 9 and subtract 11 thirds, okay? And if I do the math, that would be 27 thirds minus 11 thirds. I get 16 thirds. This is its position, all right? This is its position at time 1, okay? What would I do if I wanted to find out its position at time 5? I would do the exact same thing. I would find the integral from 0 to 5, okay? Because I knew where it was at time 0, this is going to give me the displacement if I do this, all right? And I'm not going to go through that one. It's a very similar problem. But what if they ask you to find the total distance the particle traveled from t equals 0 to t equals 5? Well, if they ask you to find the total distance the particle traveled, then I am going to integrate the absolute value of that function. And that's what changes. you have to pay attention to whether it's asking you for its location or whether it's asking for the total distance. If it asks for total distance from t equals 0 to t equals 5, you integrate from 0 to 5 the absolute value. Now, do you remember what our function looked like a minute ago? I told you, or I gave you a quick sketch of the graph that said it looked like this, okay? And we looked at it from 0 to 5, and we said this point was 1.2545, okay? Well, what I want you to remember in terms of integrals is that this area down here is negative, and this area up here is positive. So if I'm going to do the absolute value of this thing, I have to change the sign of this part right here. Well, how do I do that? I would break it into two integrals. I would find the integral from 0 to 1.2545 of that velocity function, okay? And whatever I get there, I'm going to multiply by -1. Why? Because we're finding the absolute value of it. Okay? Whatever I get, okay, for the integral of this part, I multiply it by -1, and then I would add it to the integral of this part over here. So I would add it to the integral from 1.2545 to 5 of the velocity function. So I would add it to that. And that would give me my final answer. All right, so you have to consider what the function looks like, because if it has some negative area, then you have to multiply that area by -1. And we get our limits of integration by finding out where the velocity function is equal to 0. Now, I went through all that because sometimes you may have a graphing calculator, sometimes you may not. If you have the graphing calculator, then you can use f and int and integrate the absolute value of the function, all right? And you could just do it from 0 to 5. That's if it's a question where you're permitted to use the graphing calculator and its features. And we will stop there for today.